If we evaluate the equation x squared plus 1 equals 0, isolating the variable gives us x squared equals -1. Within the standard real number system, this creates a roadblock. If you square a positive number, you get a positive result. If you square a negative number, the negatives cancel, and you still get a positive result. The equation remains unresolved. To solve this, mathematicians defined a new unit. They declared that the square root of -1 would be represented by the letter I, the imaginary unit. Defining the imaginary unit allows the single, rigid track of the one-dimensional number line to unfold into a two-dimensional coordinate plane. This provides the foundation for a system that extends beyond the limits of real numbers. By definition, if I equals the square root of -1, then I squared equals precisely -1. This specific identity is the operational engine for all complex algebra. When we map out higher powers of I, a strict pattern emerges. I to the first power is I squared is -1, I cubed is -I, and I to the fourth returns to +1. Because of this predictable loop, evaluating high powers of I relies on a simple shortcut. You divide the exponent by 4, and the remainder dictates the final value. Take I to the 57th power. 57 divided by 4 is 14, with a remainder of 1. Therefore, I to the 57th simplifies to I to the first power, which is I. No matter how large the exponent, the imaginary unit remains tethered to this repeating four-step loop. Every complex number is written in standard form as z equals a plus ib. It is a composite of two distinct parts, a real part, a, and an imaginary part, b. A frequent error in examinations is including the I when identifying the imaginary part. The imaginary part is strictly the numerical coefficient. In the number 7 minus 9i, the real part is 7. The imaginary part is -9. Including the I in the imaginary part, writing -9i, is incorrect. These components can also exist in isolation. If the imaginary part is 0, the number is purely real. If the real part is 0, the number is purely imaginary. When both the real and imaginary parts are 0, we arrive at the zero complex number, 0 plus 0i. The letter I functions as a structural marker. It is the real coefficients that govern the position and magnitude of the number on the plane. Because these components represent different dimensions, the rule of equality requires that real and imaginary parts be evaluated independently. Two complex numbers are only equal if their corresponding components match exactly. In 2x plus 3i equals 8 plus yi, a vertical line separates the components. X is 4, y is 3. Addition follows this segregation. Adding 3 plus 4i to 2 minus 5i, real parts combine to 5, imaginary to -i. Result, 5 minus I. Real and imaginary components behave as orthogonal dimensions. They flow parallel to each other without mixing during basic addition. Multiplication follows standard expansion rules, but with a specific mechanism that shifts the values between dimensions. Multiplying 2 plus 3i by 1 plus 4i yields 2 plus 8i plus 3i plus 12i squared. Here we replace I squared with -1, transforming it into -12. Consolidating terms gives a final result of -10 plus 11i. By squaring the imaginary unit, multiplication shifts values from the imaginary dimension back into the real dimension. Complex division is a structural process. The objective is to remove the imaginary unit from the denominator of the fraction. To do this, we multiply the expression by the complex conjugate of the denominator, using the difference of squares to eliminate the I. For 3 plus 2i divided by 1 minus I, we multiply both the numerator and denominator by the conjugate, 1 plus I. The denominator resolves into 1 squared minus I squared. Replacing I squared with -1 simplifies to the real number 2. Using the conjugate is the tool used to strip the imaginary component from the denominator and return the expression to standard form. Beyond algebraic notation, a complex number a plus ib is identical to the ordered pair ab. This ordered pair functions as a coordinate, establishing complex numbers as physical locations on a plane. On the Argand plane, the horizontal represents the real axis, the vertical represents the imaginary axis. 4 plus 3i is coordinate 4, 3. -2 plus 5i maps to -2, 5. -3 minus 4i sits at -3, -4. In this way, every complex mathematical operation perfectly corresponds to a dynamic physical translation across this entire two-dimensional geometric space. This geometric perspective reveals the position of the one-dimensional real number line within the larger plane. Every real number has an imaginary part of 0. For example, 5 is written as 5 plus 0i. Thus, the entire real number line sits exclusively along the horizontal axis, confirming that real numbers are just a single-line subset within the two-dimensional complex plane. For examinations, the logic remains consistent. Separate the real and imaginary components, apply the rotating cycle of powers, and use the conjugate on denominators. Ultimately, defining the imaginary unit provides the crucial geometric framework required to freely operate far beyond standard one-dimensional limits.
An imaginary number starts with a strict, absolute definition. I squared equals -1. IIT JEE problems typically present these as algebraic strings. However, relying solely on symbol manipulation can lead to rigid, time-consuming calculations that obscure the faster patterns required for the exam. To solve advanced problems efficiently, you have to stop reading equations and start seeing them as deterministic spatial coordinates. This visual translation happens here, on the Argand plane. The horizontal axis measures the real component, and the vertical axis measures the imaginary component. Under this framework, every complex number, written as z equals a plus ib, acts as a precise set of coordinates. Take 3 plus 2i. The real part is 3, the imaginary part 2, mapping exactly to the first quadrant. -4 plus 5i lands in the second quadrant. -2 minus 3i drops into the third, and 6 minus 4i locks into the fourth. Once mapped, standard operations like addition, multiplication, and division cease to be abstract algebra. They are explicit instructions for translating, scaling, and rotating these points across the grid. Mastering the Argand plane equips you with an intuitive geometric architecture. It replaces rigid memorization with fast, verifiable problem-solving. Every coordinate on this plane behaves as the endpoint of a directional line anchored to the origin, a position vector. For the complex number 3 plus 4i, this vector points from 0, 0 to the coordinate 3, 4. The exact physical distance from the origin to this point is called the modulus, denoted as the absolute value of z. Because we are on a standard coordinate grid, we calculate this distance using basic geometry. The vector forms a right triangle with a horizontal base of 3 and a vertical height of 4. By applying the Pythagorean theorem, the length of the hypotenuse, our modulus, equals the square root of a squared plus b squared. Plugging in our specific values gives us the square root of 9 plus 16. The modulus is exactly 5. Because the modulus measures a physical length, it is strictly non-negative. A distance cannot be less than 0. This physical framing immediately clarifies algebraic rules. The property that the modulus of z times w equals the modulus of z times the modulus of w simply means that multiplying complex numbers scales the lengths of their vectors. The modulus strips away the two-part complexity of the number, reducing it to a single absolute magnitude. It provides our first geometric anchor, length. Next, we apply a core operation called the conjugate. Algebraically, this reverses the sign of the imaginary component. Visually, the conjugate executes a precise mirror image reflection of the vector straight across the real axis. 3 plus 4i drops directly to 3 minus 4i. This operation is a spatial reflection, projecting the vector across the real axis while maintaining its horizontal position. Because it's a pure reflection, the new vector is exactly as long as the original. The modulus of z equals the modulus of z bar. This symmetry leads to a crucial question. What happens when we multiply a complex vector by its own reflection? Expanding the product of a plus ib and a minus ib clears out the middle terms. The I squared converts to -1, eliminating the imaginary components entirely. We are left with just a squared plus b squared. Notice that this resulting expression is exactly the square of our modulus formula from earlier. This yields the master identity for IIT JEE problem solving. Z times z bar equals the modulus of z squared.
This is why multiplying by the conjugate instantly rationalizes the denominator in complex division. You are mathematically forcing an imaginary vector to become a real squared distance. The conjugate acts as a reliable mechanical bridge, converting two complex parts into one tangible, measurable real number. Knowing a vector's length is necessary, but distance alone cannot lock down a coordinate. A length of 5 could point anywhere in a circle. We need exact orientation. That orientation is defined by the argument, theta. It measures the angle formed by sweeping an arc from the positive real axis up to our position vector. For 1 plus I, that angle is 45 degrees. To keep mapping consistent, we use the principal argument. By convention, this angle must always be strictly measured between negative pi and positive pi, which brings us to the single most common conceptual trap on the exam. Many students will blindly apply the formula, theta equals the inverse tangent of b divided by a, treating it as an infallible algebraic rule. Let's test that rule on a new coordinate, -1 minus I, resting down here in the third quadrant. If we plug our a and b values into the inverse tangent formula, the two negatives cancel out. The inverse tangent of 1 equals 45 degrees, but that is wrong. 45 degrees maps to the first quadrant. It points in the completely opposite direction of our actual coordinate. The pure algebra fails here. A numerical ratio cannot distinguish between diagonal quadrants because the double negative masks the spatial reality. The required geometric fix is to manually locate your coordinates quadrant on the Argand plane before you even begin calculating the angle. By acknowledging the third quadrant, we measure the arc clockwise from the positive axis. The true principal argument is -135 degrees. The argument calculation proves that ignoring the Argand diagram and relying solely on equations will yield answers that are algebraically sound, but geometrically disastrous. Once we have derived the exact length of the position vector and its exact orientation, the traditional Cartesian grid becomes obsolete. We no longer need to track how far left, right, up, or down a point sits. We can dissolve the grid entirely. The complex number is now fully defined by just two parameters, its modulus, r, and its argument, theta. This shifts our foundational equation into polar form. Z equals r times the quantity cosine theta plus I sine theta. Applying this to our first quadrant example, 1 plus I becomes the square root of 2 times cosine 45 degrees plus I sine 45 degrees. In polar form, complex multiplication and division streamline into basic arithmetic. You multiply the lengths and add the angles, bypassing the need for polynomial expansion. Elite speed in IIT JEE complex numbers comes from shifting frameworks, moving past rote algebraic memorization to fully embrace deterministic visual logic. Mathematics at the highest levels of competition relies on recognizing underlying architecture. Take the quadratic equation, for example. In its standard form, ax squared plus bx plus c equals 0, the variables form a precise fixed structure. To solve for x, the standard curriculum teaches a universal tool, the quadratic formula. In elite competitive environments, like the IIT JEE, relying on this formula as a default mechanism often leads to failure. The calculations are slow and prone to arithmetic errors under pressure. Algorithmic calculation obscures how the numbers actually relate to each other. Mastering these problems requires mapping the structural symmetry of the roots to bypass the speed limitations of brute calculation. Reverse engineering the equation from first principles creates a mental model built for speed and precision. Before manipulating the roots of a quadratic, we must establish their mathematical typology. We need to identify the number system they occupy. Stripping the quadratic formula isolates the core, the discriminant, delta. This switchboard dictates root behavior. Greater than 0 yields two distinct real roots. Exactly 0 means one converged real root. A negative discriminant forces roots off the 1D real line onto a 2D complex plane. The math expands its geometry to include complex numbers, ensuring that solutions always exist. The fundamental theorem of algebra dictates that every quadratic equation has exactly two roots, regardless of the number system. Solving x squared plus 4 equals 0 yields positive and negative 2i. Graphing reveals perfect symmetry. With real coefficients, complex roots lock into conjugate pairs. If one root is 4 plus 3i, the second is guaranteed to be 4 minus 3i. This mandatory paired symmetry cancels out the imaginary components during calculation, allowing the equation to maintain real coefficients while operating in the complex plane. Beyond finding the roots themselves, we look at how they interact to build the equation. Expanding the factored equation and grouping the x terms reveals the coefficients mechanics. Aligning this derived structure with the standard quadratic equation proves a direct link. The sum of the roots equals negative b over a, and the product is exactly c over a. Note the sum formula carefully. Dropping the negative sign in negative b over a is a frequent point of failure in competitive exams. Vieta's formulas provide a direct path to the sum and product of the roots, bypassing the quadratic formula entirely. To solve for alpha squared plus beta squared, finding exact roots first is inefficient. Instead, use polynomial expansion. Rewrite it as the sum of alpha and beta squared minus 2 alpha beta. Now, simply plug in the sum and product values from Vieta's formulas. We can apply this same logic to fractional expressions, like finding the value of 1 over alpha plus 1 over beta. Combining the fractions algebraically transforms the expression into alpha plus beta in the numerator over alpha times beta in the denominator. Any mathematically symmetrical expression involving the roots can be manipulated into a combination of just sums and products. Exploiting this structural symmetry reduces complex root relationships to basic coefficient arithmetic, providing the speed necessary for elite exams. The final application of Vieta's framework is construction, building the full quadratic equation when only the roots are known. We use a universal template, x squared minus the sum of the roots times x, plus the product of the roots equals 0. We can test this with the complex conjugate roots, 4 plus 3i and 4 minus 3i. To find the sum, we add them. The positive and negative imaginary units cancel, leaving 8. To find the product, we multiply them using the difference of squares. This gives 16 minus 9i squared, which resolves to 25. When these values are inserted into the template, the final equation is revealed. X squared minus 8x plus 25 equals 0. If an exam problem demands a leading coefficient other than 1, the entire structure must be multiplied by that factor. These are the two primary tools for elite quadratic problem solving: discriminant analysis for root typology and Vieta's formulas for structural manipulation. Mathematical mastery involves recognizing the symmetrical architecture that governs the numbers, rendering brute force algorithms unnecessary.